Katz from the University of Illinois, who will talk about philosophy of systems and game theories with defects.
Thank you, David, and thanks to the organizers for the invitation. I wouldn't miss this. This occasion to celebrate Ron's 60th birthday. I've known Ron for quite a while. In fact, 60 is a large enough number. I've known most of your life, right? So this is a talk. It's mainly inspired by physics. And the questions are. So I want to study the singularities of F-theory and something called T-brains. And I'll say what these mean. But I've been asked many times over the years, how does a mathematician learn physics? And the answer is always the same. Well, first you learn Hodge theory in the 70s and 80s, and then everything just happens. So I guess that's what we're doing here today. And throughout the talk, there's going to be lots of times you'll see Ron's influence throughout the development of the subject and things throughout this talk. So that will come up, and we'll talk about it. And I'll say this is joint work with Laura Anderson, Jonathan Heckman, and work in progress with them, and Laura Shakoznik. So what is, and then so for this talk, I guess I'll be talking about F-theory in 6 dimensions, which means a Calabi-Yau threefold, elliptically fibered Calabi-Yau threefold. So I'm going to be talking in the language of mathematics. I did notice some physicists in the audience. Questions are invited because these questions are inspired by physics, and many of those questions will get obscured in the way I'm developing this talk. So I have an elliptically fibered Calabi-Yau threefold. And so B is a surface, and inside there we have a discriminant over which the elliptic vibration becomes singular. And the discriminant can be a union of components. And then in this theory, what we have is D7 branes, which are, I'll try to explain what they are in our context, D7 branes. And so, for example, we can do this, we can have a Weierstrass vibration to describe this. So in F on coordinates, F is a section of -4 times the canonical bundle, and G is a section of 6 times the canonical bundle. And, okay, I just realized I was just looking at a preliminary set of notes, which I'm getting very confused. Apologize. So let me specialize to the case of where B is a Hertzberg surface, F12, to say just what the conundrum was that set us thinking about these questions. So in the case where B is the Hertzberg surface, F12, we have a section. We have a section of the Hertzberg surface and a disjoint exceptional section, which is the section of self-intersection -12. And we can go ahead and write this equation, in this case, as y squared equals x cubed plus, for f, I could take z equals 0 to be some equation for this section. The subscripts of the polynomial f is just a degree in P1. This is a homogeneous polynomial degree in P1. And then for G, we can specialize to a degree 12 polynomial in P1 times this equation of the section plus e to the 5th times G24. So let's take this section. I realize is this legible down in front still? No, it's too low already.
Z cubed was F2.
F20, FD is just a homogeneous polynomial on P1 of degree D, pulled back to the Hertzberg surface. So I'm building sections of the canonical bundle. This is the customary way it's written in physics. I'm writing this in affine coordinates. I'm just writing affine coordinates. I can go ahead and realize these as sections of the bundle I claim this in by putting in other multiples of the equation of E. I'm just suppressing those. It doesn't describe this. So if we look at this, what we see is that we have this a curve given by x equal y equals z equals 0, along which we have singularities. And we can see that the singularity type is an E7 singularity. So here I have an E7 singularity. I have a square, cubic, and fifth power. I'm sorry. Yes, that's E8, but there's also z cubed x to the next. This is an E7 singularity. This way. Which way is better? So let me just zero in on those terms. If I have, I'll have y squared equals x cubed, ignoring the higher order terms, plus f20 z cubed x, plus g24 z to the fifth. This makes the E7 a little bit more apparent here. And now this is fine because now it's an E7, so what we'll have is the discriminant locus will contain the section H at which z equals 0, but then I also have another component. And this other component of the discriminant will intersect this at the locus where f20 equals 0. So at that locus where f20 is 0, this goes away and now it looks like an E8 singularity. So this is a nice canonical singularity, and this is allowed as a singularity in that theory. But now let's take this worse. Let's now say that f20 is identically 0. So then what I have is y squared equals x cubed plus g24 z to the fifth. So now here, in this case, away from the zeros of g24, this is an E8 singularity. Nice E8 singularity. But now when g24 is equal to 0, this is not Calabi, it's not canonical. So we wouldn't be thinking about this as a good Calabi-Yau manifold. That has no canonical singularities. But still, F-theory makes sense. F-theory is known to be good here because there's a heterotic dual. And in fact, the heterotic dual description of this is equal to the tangent bundle of the K3, where the K3 is given by another elliptic surface, elliptic vibration over P1, where the coefficients are F8 and G12. So the question is to understand a little bit more systematically what's going on. How can we look, without knowing the heterotic dual, how can we look at this and understand the singularity and then it's okay to look at? Okay, so to start looking at this, I want to take a step back.
You're kind of lost in this story. Why are you modifying the y stress vibration?
I'm not, this is a bar stress vibration.
But what is that y square? The one that you wrote down.
So this is, so the standard pictures I have is that the bar stress vibration is in a projected bundle over the base, where the projected bundle has coordinates x, y, and z. So, in want to review Ron's work with about the Calabi-Yau integrable system. So here, let me step back more generally. So to go ahead and understand this, motivations come from F theory, but I'm going to describe it, what we're doing, most of this can be seen in the language of 2A string theory. So I'll say a bit about the Calabi-Yau integrable system in 2A string theory, is that here, suppose we have a complete family of Calabi-Yau threefolds, parameterized by some base. So the fiber is a Calabi-Yau threefold, and we extend this by looking at the set of pairs consisting of a Calabi-Yau threefold together with a holomorphic threefold, and pull back the system to here. And then we can form the relative intermediate Jacobian of this family, where the fiber over B and omega is just the intermediate Jacobian of XB. And what they prove is that this is an analytic, completely integrable Hamiltonian system. So each of these, the base, the complex structure moduli space has dimension H21, plus one dimension for the holomorphic freeform, and the intermediate Jacobian of the Calabi-Yau has dimension H21 plus one also. So now, in 2A string theory, so the moduli of 2A string theory is a quantum corrected version of this. So what we're going to do is, for the purpose of this talk, I'm going to treat this system as if it's the moduli space of type 2A string theory with no quantum corrections. Okay, and now what I want to do is I want to ask, what happens as we approach a singularity? What happens to this? So what happens to the moduli of 2A string theory or the moduli of F theory as the Calabi-Yau becomes singular, as we saw in our example? And this is what I want to understand. And since the intermediate Jacobian is related to cohomology, we see that we're going to be looking at variations of Planck structures, or at least half of it. Okay. So in this language, in the language of string theory, the base, in physics language, the base would correspond to NS moduli, and the fiber would correspond to Ramon moduli in 2A string theory. And I might use that language direct. Okay. So in doing this, what I want to do is I want to go ahead and compare the local geometry near the singularity to the global geometry. And the local geometry is studied in many places. So, for example, Diakonescu, Nagy, and Pantev studied the local geometry of the system and the connection between these ideas. I'll say what their result is in a second, but let me just give the A1 case for concreteness. Yes. Yep. Right now, I am going to do compact Calabi-Yau. So right now, I'm going to the local case now. So I've been talking about compact up until this point. Okay, so now what I want to do is I want to understand the local geometry and put it in the global geometry. Okay, so in the local case, if we look now at the total space, if we have, let's say, a curve, and we look at this total space of the cube of the canonical bundle, we can go ahead and build a singularity as xy equals z cubed, z squared. This is a family of Calabi-Yaus which have a singular curve of A1 singularities.
What's the relation between the coordinate and the canonical?
X, Y, and Z, so there are three.
What's the section of the canonical?
What is a section? So X, Y, and Z. I'm taking the set of everything in this canonical bundle which satisfy X, Y equals Z cubed. So X, Y, and Z are local sections of the canonical bundle. No, Z is also, there are three. K plus K plus K. X, Y, Z. So I could deform this, for example, by adding something that pulls back from 2K. Now this equation makes sense. I'm looking at all points in K plus K plus K that satisfy this equation.
So what's the dimension? It's in K plus K plus K.
K plus K plus K is a four-dimensional space that's over a curve.
Over a curve.
It's the total space of the rank 3 bundle over a curve. So I'm looking at a Calabi-Yau hypersurface inside a fourfold, and by a junction, this is Calabi-Yau. So the base of this family, this is a family of Calabi-Yau threefolds parametrized by sections of 2K, which is also the base of the Hitchin system. And what they do, they do this construction more generally. For more general curves of ADU singularities, and what they prove is that for these, the locally defined Calabi-Yau integrable system for this family of threefolds is isomorphic to a relative prim fibration for Camaro covers. So in the case of SU2, Camaro cover and the spectral cover are the same thing, and the Hitchin fibration is a torsor over this. By other work of Brian. Okay. So the takeaway from this is that the mixed Hodge structure, the limiting mixed Hodge structure, connects to the Hitchin system, which is roughly what physics tells us. So I'm paraphrasing. This is just another just reformulation of what this is. There's a direct connection in a way that can be quantified between the limiting mixed Hodge structure and the Hitchin system. So now I want to generalize this, or extend this, and then globalize. So what if instead of having a curve of pure ADE type, we have a curve, another curve of canonical singularities? So a curve of ADE singularities that can get worse. At finite many points. As for example, we saw the case of an E7 that when f20 is equal to 0, it becomes an E8 singularity. So how do we do this? And let me just give the simplest case is where I have, again, just do this locally first, and I'll do this in an affine coordinate t. So suppose that I have a coordinate t along the curve, a local coordinate on the curve c. So when t is not 0, I have a curve, this is a curve of A1s, but it becomes an A2 singularity when t is equal to 0. So how do we go ahead and understand what this is? Now let's try to do deformation theory. The sheaf T1 of deformation theory is just O of the Calabi-Yau modulo the Jacobian ideal of this curve. And the space of first order deformations are just global sections of this. And so I just have to compute partial derivatives, which are yx 3z squared plus 2tz and z squared. So here's a sheaf that's supported on the curve, on the singular curve that controls the deformations. But now the interesting thing about this is that this has a torsion section. Right? Because z is annihilated modulo the ideal by x, by y, by z, and by t, because t squared you can check from this relation. I'm sorry, but from this relation you see that t sub z is in there. I've got it, okay. That's okay. So t times z is in the ideal. So z is torsion supported at x, y, z, t equals 0. The intermediate Jacobian of this I did not find. So the intermediate Jacobian was defined in the local case using some careful topology and understanding the difference between homology and cohomology when you don't have Poincare duality. So there was a definition, which I'm not going to repeat, of how to define a local version of the intermediate Jacobian for this case. So in this case, in their case it was compact, that was pure weight 3. As I'm about to say, here we have a weight 2 component, it will be, a weight 2 part will be non-compact. And the non-compactness will correspond to this torsion line. So, and what we see here is that T1 modulo the torsion is just O of the curve. Because once I put in z, I just have x, y, z as the equation of the curve. So now let me do this a little semi-globally. Now let me take a divisor on the curve C, and I allow this to happen at finitely many points of the divisor. So I want to look for a curve of A1 singularities which can degenerate at the points of the divisor D. And I do the same analysis. This is now on a compact Calabi-Yau threefold. Because the torsion, T1 is just supported in the neighborhood of the singularity. This is a local population in the neighborhood of the curve. Even though x is compact, it doesn't matter. And what you calculate is that the quotient is locally free and identify that the sheaf rather than 2Ks, we have the patient system, we have this, something you're familiar with. And this torsion is supported at the points of D. So now if we want to do first order deformations, so here's first order deformations of X. There's a global to local map and I've just identified what T1 is, so I can compute this. To globalize, we still have one thing to worry about. I'll get to that later. So for right now, these are just potential localizable deformations. They have to be killed by this map. We don't know it yet. So in the case of the local work, this is 0, and everything's localizable because it's supported on the curve. Okay, so here to go ahead and compute this H naught from this exact sequence, let me let D be the degree of D. And I'll count dimensions. Here I have D dimensions. And here I have 3G minus 3 plus D dimensions. So what I get is that this space is 3G minus 3 plus 2D dimensions. And now I want to describe what the RR moduli are associated to this, what the intermediate Jacobian contributes to this. So as I go ahead and take a family, degenerate this, I want to be able to compute the limiting mixed large structure and identify those moduli. Okay, so I want to compute the limit of intermediate Jacobians in the degeneration by a limiting mixed Hodge structure. So I take the limiting mixed Hodge structure and I form an intermediate Jacobian out of that by just using half of the limiting mixed Hodge structure, rounding out by derivatives. So there's a kernel here. These are H1 of the, this is H1 of the tangent sheaf. These are deformations that preserve the singularity. So what's going to happen as I do the Hodge theory analysis, I'll take a family and I have to find a normal crossings degeneration. So I have to blow up. We're not going to get normal crossings because of this singularity. So when we blow it up, the exceptional divisor over the curve becomes a conic bundle. That's, the equation is there. We have xy equals z squared. But then at the finitely many points where it becomes A1, the conic bundle degenerates to a line zero. So over the points of D, we have a line pair, and we have this, and this is sitting inside the blowup of X. But there's another component that comes from the exceptional divisor of the blowup. This is a threefold. It's a quadric surface bundle over C. And over the points corresponding to D, the quadric surface bundle degenerates to a rank 3 quadric singularity. So we have a quadric bundle that looks like this, degenerating to this over finite many points. So what's going to happen is that we see when we go ahead and start computing the limiting mixed Hodge structure, we're going to be computing the cohomology of this space. And now we can see the prim visible in here. If we take the difference of the lines on the ruling, these are exchanged by monodromies, so we have to look at odd cohomology in the odd H1 in the base, and what we get in the threefold. And what we see is that H3 of Q will yield the prim variety of this double cup.
But what's the significance of this union?
The union is that behind the scenes, I'm making a choice, which I haven't told you, of what the limit I'm taking as I approach the singularity. So in other words, I guess maybe I have told you implicitly, as I'm taking some omega 2. So let me just write it down. I'm taking something that would look like z z cubed, sz squared, where s is a section of O of d, and some omega 2, which is a section of O of 2k plus d. T is bad t. I used t before, but now t is my degeneration parameter, my limiting Massage structure. So I'm going ahead and I'm looking now, if I take this, so I'm trying to understand what the limits are here. So I probe it by taking the degeneration that I just described, and now take the limiting Massage structure for this family. If I want to go ahead and achieve normal crossings here, I blow up x equal y equals z equals t equals 0, and I get a quadrant bundle, which as long as omega 2 is not 0, is rank 4, but when omega 2 is equal to 0, it's rank 3.
So that's the thing on the right.
That's the thing on the right.
And that's what's the thing on the left.
Well, that's the proper transform of the compact x. I'm back in the compact case now. So I'm taking the compact example where the curve of singularities is this local form. I'm not claiming that these are globalizing. They're not. General. So I'm just taking a compact Calabi-Yau threefold containing a curve of A1 singularities, which becomes A2 at final many points. And I'm taking a degeneration, which a global degeneration exists. I haven't proved that yet. If I have time, I'll explain why you can globalize. And then then calculate the limiting structure for that. Okay, so from the geometry, we can see this this prim coming in, and this comes in the third graded piece of the Massage structure, but also we have a weight 2 part. And in the calculation of the weight 2 part of the part structure, we turn out here we get the contributions of C star for each of the points. So let's count moduli over here. Here the prim we can compute is 3g minus 3 plus d dimensional. This is d dimensional. So altogether we have the 3g minus 3 plus 2g local moduli that we were expecting to find in this. So in a compact example, we can go ahead and describe. There's a map from the moduli of some compactification, which we do not describe globally at this point, but we're just saying now there's a projection from those moduli to these moduli that are detectable in the compact map. Okay, so now, if you're a physicist, this is not a surprise, because what a physicist will tell us is that this theory is described by an SU2 gauge theory with G adjoints, and D fundamentals. And so if you have a theory of this, you can go ahead and compute how many deformations there are by just counting the dimension of the Higgs branch. And the dimension of the Higgs branch is very easy to compute the dimensions of in theories with n equal 2 supersymmetry. We take the total dimension of these representations. The adjoint representation of SU2 is 3-dimensional. The fundamental representation of SU2 is 2-dimensional. And the Higgs mechanism gives a mass to the bosons in SU2, so they're gone, we subtract 3. So what physics tells us is not only should we have some system like this, but it should be described by gauge theory, and it's globalizable, because there are no obstructions from n equal 2 supersymmetry. So what I'd like to describe is the connection between this gauge theory and what I just showed, and then how to globalize.
So these Higgs bundles are supported on these things are clear.
Yeah, there are Higgs bundles, there are Higgs-like bundles. They have defects because they can have poles at the divisor.
What is globalized?
By globalizable, yes, sorry for being sloppy here, is that what I have is I've given a description of a gauge theory on the curve. The way I've described it, this doesn't see anything about the compact geometry. And the assertion is that I've described the local deformations from the gauge theory. And the assertion is that there's a global deformation of the Calabi-Yau that realizes this deformation. Or said differently, in terms of this map that I almost erased, for the deformations I just described, this map is 0. This is not true for arbitrary singularities, obviously. But for these kinds of singularities, the Calabi-Yau and these singularities make the deformation globalizable. So it's kind of like, in a sense, it's like unobstructedness of Calabi-Yau moduli space in some form. It's a little different, but it is related to that. In fact, my argument to that will be related.
You also asserting some objectivity that as you vary the Calabi-Yau, the data on the curve has to change.
Yes, yes. As you vary the Calabi-Yau, the curve will generically disappear. Which is, in fact, how I can do the calculation. Because I have tamer singularities, or I can even smooth it, so I can compute everything in such numbers. Right. But, so in other words, so what you proved is that this, I may have left off an important point, is that the Calabi-Yau integrable system is isomorphic to the prim system away from the discriminant locus. And this context is precisely the discriminant locus I'm trying to put. And I can't, and I don't know, the compactifying moduli of complex varieties is interesting enough. Compactifying the Jacobian vibration is even more interesting because then there's monodromy, and what does this even mean? So in the absence of doing that, what I'm doing is I'm explaining how to go ahead, just like we can do with Hodge theory, is how to use limiting mixed Hodge structures to go ahead and just see where these moduli go as I smooth. Okay. So now, what is the gauge theory? So in the gauge theory description, I have a P is a principal G bundle. We could think about G as SU2, or SL2C, specified. So let V be the fundamental representation. Fundamental two-dimensional representation. Maybe I should say SUN so I can do it a little more general. Okay, and then we have inside here a Higgs field. Which is allowed to have poles, simple poles along the divisors of D. So these are our adjoints, and our fundamentals are in the fiber of P tensor V at my points Pi, so let's think of D as a sum of Pi's. And then I have dual. So this combination is what's meant by is representing a hypermultiplet. And the gauge theory description is simply that the residue of phi is equal to psi I tensor psi I conjugate. After all, the adjoint, remember that the adjoint representation is with a trivial factor is just V tensor V2. So this is what physicists tell us is the gauge theory description of the system. And now what we can see in the case of n equals 2, what we see is that since this has rank 1, this is a 2 by 2, we can think of this as a 2 by 2 matrix that has rank 1 because it's decomposable. It's a tensor product of two objects. So this tells us that the determinant of I lives as a section of h naught of 2k, but only first order k. Also,
This is for n equals 2?
yes, sir.
This is only for n equals 2?
This is on,
For n equals 2 or all things?
I'm sorry.
Your group is SUN or SU2?
This is SU2. For SUN, I would take the whole characteristic polynomial. So for SUN, then what I would get is I would have the characteristic polynomial would live in the sum from j equals 2 to n of h naught of jk to d. Always first order pole because this is rank 1. And the thing that's interesting about this description is that this matrix, it's rank 1, but it need not be nilpotent. This can have a trace. This is what corresponds to the torsion in T1. So it's a perfect match. And now if we mod out by this torsion, if we mod out by the trace, then we're looking at PSU2 bundles and we're back to the adjoint group. And then we have the, and we see that we have this nice generalization. So what we have is the way in the geometry literature, the way this comes up, I'm not really sure. So I think I can do this. Just looking at these systems where I can have parabolic bundles. I take arbitrary line bundles in terms of k of this system. We get a Poisson structure, but not a symplectic structure. So to go ahead and embed that in a bigger system, where now we have as many fiber dimensions as base dimensions, we have a symplectic structure for business as well. To go ahead and see the C stars, the C star comes from that we can go ahead and fix all the data, we can fix the bundle. What are we changing? We can have C star scaling, psi conjugate goes to lambda psi, lambda inverse psi conjugate. So that's the extra C star degree of freedom that we can see in the gauge theory more easily than we can see in the geometry. This is stronger than the star structure. So the gauge theory geometry match can be done in as much detail as you want to. And what about globalizability? So here, so I guess maybe one more thing I should say. The statement is that I have a C star in the a C star locus in this solution space of this gauge theory, which fixes the characteristic polynomial. So notice it fixes phi. So if I'm fixing phi, I fix everything that we would previously know to do, that we used to do in geometry. This fixes the characteristic polynomial, this fixes the spectral cover, this fixes the Higgs bundle, this fixes everything by fixing phi. What extra freedom do I have? I can't change the residues, but I can go ahead and rescale each side conjugate independently. That's my C star that we didn't see from classical geometry until we started to look at the Homologous structure.
So this arrow is linked to adding data?
This gauge theory adds data to the system we study, yes. And this is the gauge theory that F theory tells us to study. So maybe another viewpoint into how we can do this by so suppose I had this deformation. How do I see the torsion deformations? Well, the torsion deformations, I can go ahead and add the term omega 1z, where omega 1 is a section of k plus d. Now, this may look like a funny thing to do with a quadratic deformation because we always complete the square. But we can't at the zeros of s, where s equals 0 is d. So everywhere away from d, this goes away by a reparameterization. So I call this a torsion deformation because it's only at d that this really has first order substance. So here, in writing down a geometric deformation, for example, if this came from F theory, we would have this as a local equation by expanding my F and my G, and so and all these terms would be there. But if I want to count moduli, we have to do it correctly. And so it's only the restriction of this section to D by residue, which makes sense. And luckily, the geometry tells us exactly the same thing that the gauge theory tells us to do. Well, not luckily, but geometry and physics always have to say the same thing, where you have to go ahead and correct your dictionary. So to do globalization, this is really again, these are Hodge theory from the 70s and 80s. So let's look at our blowup now, and inside our blowup we have this conic bundle. And we had these first order deformations. We have some potentially operational K. And then we have an Alba Jacobi mapping. So by the unobstructedness of Calabi-Yau moduli, we get G moduli. We get G global moduli. So we have to show this mapping is injective, but it is. And we get G global moduli. And now what happens if I take a first order deformation associated to this omega, corresponding to the one parameterized by the Alba-Jacobi mapping and the dictionary between H2-1 deformations, given the choice of a holomorphic freeform, which we have in F theory, then we can ask which of these fibers deform with our first order deformation. So called CP. And the result is that CP deforms to first order if and only if omega of p is 0. So we take this actual deformation, and we see that from here we get 2G minus 2 curves on the nearby Calabi-Yau. Okay, and now if we look at a line pair, the intersection of a line with a nearby fiber is 0. So the intersection of the line with itself is 0. With its own fiber is 0, which tells us that L squared is minus 1. So C is a curve with normal bundle O of minus 1 plus O of minus 1. And it's well known that these curves all deform. So we get 2D curves. So we have these P1s on the deformed Calabi-Yau. On the deform Calabi-Yau, we have 2G minus 2 plus 2M P1s, each of which have a normal bundle O of minus 1 plus O of minus 1. So the normal bundle is O of minus 1 plus O of minus 1. Let me assume that omega is generic, so these are simple zeros. So that's what we need to prove the O of minus 1 plus O of minus 1. Oh, yeah, thanks. 2D. Okay, and now let's blow this down. One thing, these are all homologous up to multiple. This is in the same ray in each two of the deformed these curves are all homologous up to multiple. Because of the construction, they were all homologous here, so up to multiple. So when we deform, they stay homologous. And now, an old result of Clemens and Friedman is that these now are smoothable. These singularities, these are node singularities. These are smoothable, and because there's one homology relation, there's just a one-dimensional homology space, this implies that the dimension of the smoothing is one less than this. So to get the total number of local deformations that we found, as global deformations, we now add the G that we had before, and we get 3G minus 3 plus 2G. So I claim that this is the match of parameters. So all of these parameterize the 3G minus 3 plus 2D parameters I had found before. And to justify that, you can write down local equations. What this is it's like taking z minus take z minus omega. So shift to let me just take d equals 0 just for simplicity, so I can say the point basically is that I take the deformation z minus omega squared, where omega is this section of the canonical angle. No, that's not what I wanted to say. Okay. Dave, you know what I'm trying to say?
I can't articulate it.
Yeah, I can't either. Okay. So what I'm doing is you can write down a global deformation where I can deform my curve of 80 singularities to a curve of these isolated curves. Let me just try that one more time. Maybe I have it right. Still doesn't work. No, got it. Sorry. Take my section of 2K to be a perfect square. These are the G deformations that I was doing before. Because now what you can see is this has 2G minus 2 nodes. So what I'm saying is by writing down local forms, I can match the parameters completely, at least on the complex structure deformation side, which is all on the circuit at this point. So these are my first G deformations. And then my second G would be adding on a general omega 2, but now we're looking at sections of so here's my 2G minus 3. I guess I can't see them from here. This is just taking 2G minus 2 nodes and smoothing over 2G minus 2. not going to be able to do that with such equations. So coming back to that T-brane example, let's say I take an SU2 system, and let me start with that same the same F and G that I had before. But now let's do this as an SU2 deformation with defects here. So what we have here is that now the troublesome case of F20 equals 0, we can see corresponds to a nilpotent phi. So a nilpotent phi is roughly, with some oversimplification, especially as I run out of time, as a T-brane in physics, which we wanted to understand. So if phi is nilpotent, that's F20 identically 0, we still have a gauge theory description. So the question is, what kinds of nilpotent singular Higgs bundles can we get? Well, this is something that Ron also studied with Ian and Lazarsfeld. I'm going to use different language. It's essentially what they did. Is you could take k of d to the 1/2. It's a generalization of Hitchin's explanation. Take any extension like this, and then I can go ahead and turn this into a meromorphic Higgs bundle by mapping this to k of d to the minus 1/2 tensor k, and this vanishes. I've got a sign one somewhere, which goes into d of d. I'm missing a d. Well, I have meromorphic. And now if we see that that we now have a mapping tensor k of d. That's solution. So if this is my phi, that phi squared equals 0, and this is nilpotent. So what we have is that the moduli of this system includes the RR moduli describing the bundle data. This would be H1, so H1 from this to that, which would be of minus k minus d, and this has dimension 3g minus 3 plus d. The other d degrees of freedom, we already know, are not detectable at all from the Higgs bundle. They have to come from the full gauge theory with the extra c stars. So the takeaway is that we can go ahead and take this SU2 system, embed it in the E8 gauge group, and break to E7. E7 is the commutant of SU2 in E8. So we see the structure of the E7 singularity is what tells us we can go ahead and play with SU2. And then at the same time, the fact that we can even go into E8 and have these bad places at the G24, by still having these non-trivial T-brane structures turned on, it becomes allowable, and F-theory is a sensible limit. So if I have any more time, I can continue, or I can stop here. I can stop here? Okay. Why don't I stop? Why don't I stop? Thank you.
Any questions?
So, you described the initial life, which becomes worse.
Yeah.
If it doesn't become worse, and it has a value modularity,
Yes. Which depends how they describe it. Yeah.
what happens when you get worse?
Okay, then what you have is you have a tool you can use. You can go ahead and pretend that you had a bigger group. So here you can pretend that you have an A2. And then you have a bigger eval group that doesn't extend globally, but is very helpful in the analysis at that point. So, yeah, so Yeah, so this is, well, let's say maybe without going all the way up higher, I can add a rank, and I go from SUN, and let me at least safely stick this inside UN. Because now when I have an equation that says that the residue, that the residue of phi is equal to psi conjugate, what does that even mean? This is not in SUN, it's in UN. So there are remnants of larger gauge groups that show up in the gauge theory in the physics. In the geometry, I can't give a answer to your question at all. But it's a good question, I'll think about that. It's a different group, different rank.
Other questions? Yeah.
What happened to the special random count when I close this new data?
Oh, yeah, I don't, no, I don't. Good question. But, but since this is a perfectly well-defined limit in 2A, it's, yeah, if you have ideas, let me know. That sounds interesting.
There are no, oh, sorry, there is one.
Well, you're getting the E8 versus E7 to explain that C2. Do you have any wild guesses about?
Yeah, but wild, yeah, this is what we've talked about. So wild is I could have higher order poles, then there's wild, his bundles is part of the story. But also, there's a question about how do we generalize your work on doing the SU2 nilpotent ones. So you could do this for arbitrary groups, but the classification is nice. So there's this, the problem is if you could take any nilpotent element of any Lie algebra is in the image of SU2. So, but in your case, that degenerated over finite many points, which can still happen. But in your case, the degeneration is 0, so it's still an SU. It's still the same. It can still be described in the same language. If I have the nilpotent element in SU3, let's take a rank 2 Jordan block. It can degenerate to not vanish, but to lie in the rank 1 orbit. So in principle, what you would have to do is to extend what you did by successive extensions. And I haven't been able to find a way to go ahead and give a clean normal form for all examples. But I can say anything can be represented in this form, but I don't know if everything in the form I can write down really is representable by a nilpotent angle. So I'm happy for describing everything. But then once you have any nilpotent orbit, you take the smallest Lie group it's contained in, study that, and then you can go ahead and see that in FU. So we could do that for SU3, embedding in the 8, which gets you down to E6 singularities. So that's the same thing. I guess if I do you remember the degrees for E6s? I don't either. But I can show you later. So we can certainly do SU3, embedded in D8, so you get E6 singularities, enhancing to D7.
Okay, let's thanks, Sheldon, again. Next talk at 11:30.